I'm Zhang.
I'm Wenhao Li. I'm Jiarong Zhu.
Today we'll be presenting our custom project for our Applied Deep Learning class. An exploration of generative adversarial networks for image-to-image translation. Specifically, we'll be focusing on the frameworks of Pix2Pix, CycleGANs, and units. We'll be discussing a background of GANs, as well as a theoretical perspective on Pix2Pix, CycleGANs, and unit, and the results that we achieved with our respective networks and models. Generative adversarial networks. In 2014, Ian Goodfellow and his fellow researchers at the University of Montreal published a monumentally influential paper proposing an innovative framework for estimating generative models. In his paper, he proposed a generative model G to compete with a discriminative model D to play a minimax two-player game. Goodfellow likens the generative model to a team of counterfeiters who try to produce fake currency to use without detection, while he likens the discriminative model to police who are working to detect these counterfeits. The competition between the two will force each party to improve. The counterfeiters get better at making fake currency, and the police get better at detecting these imitations until the counterfeits become so indistinguishable from real currency. These models are represented as neural networks and are trained via backpropagation. The generative model G captures a data distribution, P of G over X, over data X. A noise vector Z is introduced to the neural network and is mapped to a data space, parameterized by theta G, as G of Z parameterized by theta G. The discriminative model, which also is a neural network, is defined as D of X parameterized by theta Z. And the discriminative model outputs the probability that a sample is from the training data X rather than from P of G. Now, from the equation you see on here, this is the value function that describes the minimax game. D is trained to maximize the probability of assigning the correct labels to the samples from G and training data X, while congruently training G to minimize the log of 1 minus D of G of Z. From the images you see, these are the results of a trained GAN on the MNIST dataset as well as the TFD dataset. The rightmost column represents the closest training example of these respective datasets. All other images within these within the MNIST and TFD you see here were developed with his GAN. We're trying to approach the problem of image-to-image translation, and there are two ways to do so: supervised and unsupervised. With supervised image-to-image translation, we have paired data. So the images all come with various forms of labels, whether it be edges, as you see here, or semantic label maps. Unpaired images, on the other hand, just present two images, preferably with some underlying structure, and are vastly more difficult to learn. Although it is you have a much easier time collecting data for unpaired image-to-image translation. Paired translation represents Pix2Pix, while unpaired image-to-image translation represents what we see in CycleGANs and unit. With Pix2Pix, we're trying to investigate conditional adversarial networks as a general solution to image-to-image translation problems. We want to learn a mapping from an input image to an output image, and we want to train a loss function, and we want to learn a loss function to train this mapping. From the Berkeley paper, they were able to effectively synthesize photos from label maps and reconstruct objects from edge maps, as well as colorized images. They use and propose two unique architectures for their generative adversarial network. For their generative network, they're using UNet, which is an encoder-decoder with skip connections between mirror layers of the stacks of the encoder and decoder. For their discriminator network, they're utilizing patch GANs, which penalize the structure on the scale of patches. The discriminator determines if an n by n patch in an image is real or fake. Essentially, this also, as a generative adversarial network, is playing the minimax game between the generator and the discriminator. For CycleGANs, now we're working with unpaired, unsupervised image-to-image translation. And the approach for learning to translate an image is now vastly different than what we saw in Pix2Pix. Our goal is still, though, to learn a mapping G from X to Y such that the distribution of images from G of X is indistinguishable from the distribution Y using the adversarial loss. Unfortunately, we cannot just use this definition in this goal, because with only this goal with unpaired data, we actually converge to single solutions. Thus, CycleGANs introduces a really innovative method of cycle consistency loss. So now, not only do we have a mapping G from X to Y, we also have an inverse mapping F from Y to X in order to get this cycle consistency loss. We want F of G of X to be as close to X as possible, and we want G of F of X, G of F of Y to be as close to Y as possible. And this can be seen with the diagram here. And with CycleGANs, the researchers at Berkeley were able to work with a number of subjects, such as paintings, animals, and seasons. For CycleGANs, now we're working with 3 different loss functions. The adversarial loss, of course, is the same as before, and we're trying to train the generator to compete with the discriminator. For the cycle consistency losses, we break that up into 2 more losses: the cycle reconstruction loss and the cycle identity loss. The cycle reconstruction loss is used to find a mapping from A to B to A or B to A to B. And for the cycle identity loss, we're using that, and we want to minimize that loss for a mapping of A to A or B to B. Third architecture that we want to work with is UNIT, or unsupervised image-to-image translation. And for this methodology, their innovation is that, or the innovation that the NVIDIA researchers are presenting, or that they're now trying to learn a joint distribution of images in different domains by using images from marginal distributions of those domains. And now they're analyzing GANs and utilizing it in a more probabilistic approach. So they want to find a shared latent space in order to map from different domains x1 and x2 as seen in the figure below. And they use variational autoencoders to do so. But with this technique, they're able to change and modify various features of their input image to what their desired output image can be. From the images you see on the screen, you can see that when they input a cat or dog, they're able to change what type of cat or dog, or what type of animal they want it to be, as well as the other translations that we saw previously with seasons, or even animals, or horses to zebras as well. So with the UNIT framework, now we have 2 different encoders, E1 and E2, who are also CNNs, and we're also sharing weights between a lot of these networks now. So with E1 and E2, the CNNs have last layers that are tied, while the G1 and G2 neural networks are CNNs whose first layers are tied. When you also have X tilde 1, 1 to 1, and X tilde 2, 2 to 2, which are domain translated images, while X tilde 1, 1 to 2, and X tilde 2, 2 to 1 are reconstructed images. And like the previous models, we also have discriminators D1 and D2. With this framework, we're actually now working with 8 neural networks. And with these neural networks, we're also working with 12 different loss functions that we use to backpropagate through those networks. We have our discriminator loss, our adversarial loss, and our cycle consisting losses, as we shown before in CycleGANs. But now we're introducing VAE cycle loss and VAE losses, which definition you can see here. So the VAE loss wants to minimize the loss from a translation of A to B to E, as well as B to A to E, where A is image domain, is your first image domain, B is your second image domain, and E is your encoder. And for your VAE loss, you want to minimize the loss from A and B to this encoder. For our Pix2Pix model, we use this as a baseline to evaluate our other unsupervised approaches and to understand and to gain a better understanding of what image-to-image translation entails for generative adversarial networks. Thus, we were able to use the TensorFlow 2.0 tutorials, which was a great help to us. And with Pix2Pix, it presents a relatively simple framework. So we're only using two neural networks, the discriminator and the generator, and we also have access to label training data in order to create building facades from semantic label maps. For our generator, we're using 8 downsampled convolutional layers and 7 upsampling deconvolutional layers. For our discriminator, we're concatenating 2 images, a generated image and a target image as one input. And we also have 5 downsampling convolutional layers. And again, we're outputting the probability for the discriminator. For this framework, we're only using 2 different loss functions to train our networks, each with the atom optimizer and a learning rate of 2 times 10 to negative 4. Here are our results for our Pix2Pix framework. As you can see, the ground truth and the semantic label maps coupled together really help create these predicted and translated images. However, the semantic label maps are not perfect. Some of the structure in the ground truth is indeed lost. For the images with roofs, the predicted images are unable to determine that feature because the semantic label map is unable to classify these features. And to make this more accurate, you would have to have a better image segmentation model in order to pre-process this data. So moving on to our unsupervised approach, the first one we experimented with was CycleGANs. And as stated before, we're using 4 neural networks, 2 generators and 2 discriminators. Our generators are composed of 4 downsampled and 4 upsampled modules, utilizing the RMS prop optimizer with a constant learning rate of 1 times or 10 to the negative 3 learning rate. And our 2 discriminators are composed of 4 discrimination layers, each with a convolutional layer, a leaky ReLU activation, and an instance normalization. The discriminator optimizer is also an RMS prop, but with a constant learning rate of 1 times 10 to the negative 4. With our CycleGANs network, we were actually able to find a pre-trained network in which we use into our model, in which we use transfer learning to employ into our model. And thus, we're able to translate relatively confidently from a horse to a zebra and back to a horse, as seen by these images here. Notice that for most of these images, most of the successful images at least, have the entire horse structure shown in the image and have a good contrast between the edges of the horse as well as the environment behind it. And we believe that due to the structure of CycleGANs and its generator network, that would produce more successful data. Here are some examples of more unsuccessful translations for CycleGANs. As you can see, the horses that are black and white are unable and have not been successfully translated into zebras. And again, this actually may be likely due to the data that we have, as there might not be enough diverse data that our generator is able to determine that different colored horses are actually horses. And moving on to zebra to horses, this was actually a more difficult network for us to train because of the stark contrast in a zebra's stripes, which, as edge detection is concerned, might be a reason why our generator was unable to perform as well. However, we do show some successful examples here. But from the bottom half, you can see some unsuccessful examples where our CycleGANs network failed to convert our zebra to a horse. For units, unfortunately, we were unable to find any pre-trained models, so we had to train our models ourselves. And unit is the most convoluted of approaches that we've encountered so far for image-to-image translation, as now we're using 8 neural networks and 12 different loss functions. Well, 6 different loss functions, but 12 total losses to train our networks. In order to speed up the training of our networks, we actually changed the size of our images from 256 by 3 to 128 by 128 by 3. And here are some examples on the left of more successfully translated results. Again, you notice how most of the successful results involve the horse or the zebra being entirely shown in the image, as well as a stark contrast between the edges of the environment and the horse itself. For the unsuccessful examples, we can see that the contrast is less stark and that we're not showing necessarily the entire part of the horse. But fortunately, because we had to train this entire network ourselves, we're able to see the progression of our training through this GIF here. We also experimented with the summer to winter translation, and here are results. This was one of the more difficult translations for us to optimize because for scene images like these, the images have a lot of features, and we believe that our network needs to be trained far more efficiently in order for our generators and variational autoencoders to capture these features. However, it does do an okay job of changing what they find as green to white. And again, here is a GIF of our generator training. Lastly, for unit, we also experimented with changing an orange to an apple, which we thought would be the most simple translation to work with. And for the most part, when we just show the entire orange or the entire apple itself, it works fairly well. However, there are a lot of cases where the orange is peeled, or the apple was cut, or the orange is cut, and our data set was not diverse enough for our architecture to be able to convert these examples or these edge cases correctly. And here's another GIF of our translations. The top one being slightly more successful than the bottom. So, discussion and final thoughts. GANs was a very interesting architecture to work with, and as we worked with different architectures, we discovered the idiosyncrasies associated with all of them. However, one thing that remained stagnant through all of them was the fact that we needed to synchronize the learning and the training of our discriminator and generator networks. If one were to train or converge too fast, then the other would fall vastly behind, and the entire network would become unstable, and all of our output images would have failed. So we implemented a lot of things like adjusting the learning rate or keeping our discriminator stagnant when there's when it was outputting high probabilities, in order to make sure that these two networks were learning together. And as I discussed before, a lot of the failures in our image translation were due to the fact that our data set may not have been diverse enough. Thus, when we were trying to translate things like black or white horses or peeled oranges, we failed. And of course, we are also limited by our laptop devices. None of us have GPU machines, so we weren't unable to train for incredible amounts of time or use really large input data to optimize our networks. And when we didn't have pre-trained networks, of course, our results were not as good. And we kind of noticed that CycleGAN specifically is limited by its inability to distinguish specific features, but actually it does really well at edge detection. So long as I can detect the edge of a horse, it should be able to change the texture and color. And it really works well for texture and color. However, it does not necessarily remove or change the hair, which are different between the two animals. The unit, of course, was the most difficult network architecture to work with due to the fact that we had to balance 12 loss functions in 8 neural networks, and we didn't want any one neural network to overtake another, or else we would still converge to very unstable solutions. Thank you. If you have any more questions, please refer to our write-up, where we post more links to our generated images and dive deeper into the theory of these translation methodologies and architectures, as well as our application of them. Thank you.